Hello viewers, welcome back to this channel. This is Uace taking you through A level in organic chemistry. So this is the second video. The first video was about periodicity because periodicity is a very important topic in inorganic chemistry. So this video is suitable for both senior 5 and senior 6, and you are advised to pause the video, write down the notes on each and every slide before I start explaining them. So in this video we are going to be looking at group 7 elements, and it's going to be presented to you by me, who is Uace. So subscribe to the channel so that you don't miss out on the subsequent updates. So you're going to start with group 7 elements. Group 7 elements, you'll be provided with a periodic table in your examinations. And down the group, we have already looked at what happens already for elements, for things dealing with periodicity. So this is a brief review, and we're having atomic radius, we're having boiling point, we're having bond energy, we're having electron affinity. All these ones were explained in our first video, which was about periodicity. So in this video, we are going to be looking more in depth about the reactions and chemical properties of each of these elements together with their compounds. So we are going to have a brief review about periodicity, but explanations are going to remain the same like we had them in our first video. So we shall start with atomic radius. What do you see with atomic radius? That's happening from fluorine to iodine or down the group. So you see that fluorine has the smallest atomic radius and iodine has the largest atomic radius. And we said when you're explaining periodicity terms, like I said in the first video, the explanation is always going to remain the same. The structure of the explanation is going to remain the same. We mark specific key factors. Like whenever explaining a periodicity concept, we are always looking at effect of nuclear charge. Is it increasing or decreasing? After that will be awarded half a mark. Then we look at what is causing that change. Then that's always the reason. So we expect either use this word due or you use because. So in this factor, since we are looking down the group, we are saying that first of all, some questions require you to state and explain the trend. I already explained that in periodicity, so this side I was just giving notes without organizing. So if you didn't watch the first video, pause the video, go to playlists and watch the video that I uploaded first. It's about periodicity. So we are having our trend as atomic radius increasing down the group. And why is this the case? We have already looked at periodicity, and we say that down the group, nuclear charge increases. Nuclear charge increases due to addition of protons to the nucleus of each of the atoms of the elements that you are looking at, while screening effect is as well increasing. And for every change you talk about, you give a reason for it. Like here we say nuclear charge is increasing. Why is it increasing? This is due to additional protons to the nucleus. Screening effect is as well increasing. Why is screening effect increasing? Screening effect is increasing due to the additional completely filled energy levels of electrons. So each and every change you talk about, you must give a reason behind it. So we shall be awarding half a mark for the change you have stated and half a mark for the reason for that change. But the increase in screening effect outweighs the increase in nuclear charge. Now back in the periodicity video, I said most students make a mistake here. They say that but screening effect outweighs nuclear charge. That's very wrong. The correct statement is increase. We need to see this word increase. It's the increase in spin effect that outweighs the increase in nuclear charge. So be aware of that and take note of that. If you have in your notes, you must underline it so that you don't forget it, because these ones carry half a mark, each of them. After talking about increase of spin effect outweighing increase in nuclear charge, you must talk about effective nuclear charge. So there will be, if we have increase in spin effect outweighing increase in nuclear charge, so the effective nuclear charge we expect it to increase. That means that outermost electrons are going to be more strongly attracted to the nucleus than they are repelled. And in such circumstance, we shall lead to a decrease in atomic radius. But if increase in spin effect outweighs increase in nuclear charge, outermost effective nuclear charge will decrease. That means that outermost electrons are going to be more repelled than they are attracted by the nucleus, causing an increase in atomic radius. As I've already said, all these explanations for periodicity were given in the first video, periodicity. If you didn't watch it, pause the video, go and watch it, note down the notes and note down the key elements that I was explaining. So let's proceed. Now here we are talking about boiling points. Now boiling points are explained the same way like melting points. And when you're explaining melting or boiling points, all you need to know, number one, you need to know the structure. So you need to know the structure holding the element or the compound or the substance you are explaining has. Number two, you need to know the forces holding that structure. Forces holding the structure. That's how we explain melting or boiling points. And then you talk about what affects the magnitude of these forces. You will see that in most cases it's atomic radius or bond length. So you first state the structure, then you talk about the forces holding that structure and how the magnitude or strength of those forces is affected by any outside factor or any intrinsic factor like bond length or atomic radius. So looking at boiling points of group 7 elements, group 7 elements, most of us know that they have simple molecular structures, and things with simple molecular structures always have van der Waals forces of attraction holding them. Since it's van der Waals forces of attraction, as we explained in group 7, van der Waals forces of attraction depend on molecular size. So we shall expect fluorine to have the lowest boiling or melting point, and we expect iodine to have the highest boiling or melting point. Reason being, fluorine has the smallest molecular size. That means that the magnitude or strength of the van der Waals forces holding its molecules are going to be weaker, or are going to be the weakest. But in iodine having a larger atomic radius, it also has a larger molecular size. That means that the magnitude of the force of van der Waals forces or strength of van der Waals forces holding its molecules are going to be stronger. Hence, it's going to have the highest melting point. Let's proceed to bond energy. Now with bond energy, we are always looking at the amount of energy required to break the bond between the atoms of the molecule. If you look at fluorine, fluorine is diatomic, it's written as a molecule. So if you are looking at bond energy, we are looking at the strength of the bond between its atoms. Same applies to other elements. So we are looking at the factors that are going to affect the strength of this bond. And what you need to know about bond length is that the shorter the bond length, the stronger it is. And the longer the bond length, the weaker it is. So we expect fluorine to have an abnormally low value of bond energy. Actually, this is an abnormality. It's an abnormality in fluorine, and the reason for that is because the fluorine atoms have very small atomic radius, and on having a very small atomic radius, the bonding electrons, these ones in this bond, greatly repel each other, and since they're in constant repulsion, moving away from each other, energy required to break this bond is going to be very low. That's why at some point we shall say that the bond energy of fluorine is lower than expected because of the strong repulsion between the non-bonding electrons around fluorine atoms. And the reason behind that we have said that is due to the small atomic radius of the individual fluorine atoms, like I've sketched here. The non-bonding electrons are therefore close to each other and they repel each other greatly, causing any significant or any small amount of energy to break the bond easily. Generally, bond energy decreases from chlorine to iodine, and the reason for that is because I've explained it. Bond energy, we are looking at the factors that are going to affect the strength of this bond, and we have said that the shorter the bond, the stronger it is, and the longer the bond, the weaker it is. So let's look at the explanation. Bond energy is decreasing from chlorine to iodine. This is because from chlorine to iodine, atomic radius increases, so that nuclear attraction for the bonding electrons or valence electrons also decreases, hence need less energy to separate. Now this is an alternative explanation, but another student could say this is because from chlorine to iodine, atomic radius is increasing, hence increasing the bond length between the atoms of each individual element. And then you proceed by saying the shorter the bond, the stronger it is, and the longer the bond, the weaker it is. Hence, bond energy decreases from chlorine to iodine. Now let's proceed to electron affinity. As we have already explained it in periodicity, nothing is going to change. It's just that here we are specifically on individual elements for group 7. Electron affinity will decrease from chlorine to iodine. Now let's first remember ourselves, what does the term electron affinity mean? Previously in the periodicity video, we defined electron affinity as the energy evolved. That means that we are measuring energy in terms of being evolved or exothermic to the surrounding. That means that whenever we are going to set for such a question, we are going to attach the values, the digits or the numbers with negative values. And those negative values are simply showing you that energy is being released. So never consider negative values when you are explaining. Instead, they are telling you that energy is released. Even if they tell you to plot a graph about electron affinity, know that the negatives are ignored because the negatives are simply showing you that energy is released according to that value. So you're saying that electron affinity decreases from chlorine to iodine. And why is that the case? This is because the increase in atomic radius is in the same order. Alright, so what were the factors affecting the addition of an electron? We have said energy released when an electron is added to the atom. We say that the stronger the incoming electron is attracted towards the nucleus, the more energy is released. And once more energy is released, we expect the values of electron affinity to be higher. And thus, if the radius of the individual atoms of the elements are smaller, we expect the incoming electron to experience more attraction than the repulsion by the electrons, and it will be experiencing a stronger nuclear attraction. That means that the more stronger it is, the more energy is being released. And once more energy is being released, we expect an increased value of electron affinity. Now we are continuing saying the nuclear attraction for the electron to be added decreases. And it's decreasing because we are increasing atomic radius. Remember, as atomic radius increases, that means that we are adding completely filled energy levels of electrons. So you find that this is the nucleus, and the electron incoming is going to experience more repulsion by these electrons present on these energy levels here than the nuclear attraction which is present here due to increase in atomic radius. So as atomic radius increases, the incoming electron is going to be less attracted by the nucleus. That means that, and once it's less attracted, that means that we are going to release less amount of energy. Subsequently, the value of electron affinity is going to be low. Now there are some questions that will be telling you, explain why the fluorine has the lowest value of electron affinity. Now in inorganic chemistry, whenever you see a word why, or whenever you see a word reasons, we are asking for periodicity. I want you to remember that. We are asking for periodicity. And the terms in periodicity include atomic radius, ionization energy, electron affinity, among others. That's why if there is an abnormality in the group, we shall always refer to those groups. We are saying that it has an abnormal low value of electron affinity because of its small atomic radius. Now notice that such kind of a reply is because we didn't compare fluorine to anything else. But questions which require why is fluorine having the low value of electron affinity compared to other elements in the group? Now the answer would be is because of its very small, it has the smallest implies that it has the smallest atomic radius among other elements. That's for questions that involve comparison. So here saying that it has a small atomic radius was fine because it wasn't compared to any other element. Now we are saying, giving an explanation for having a very small atomic radius, like I told you, among the fluorine atoms we shall have strong repulsion between them. The fluorine molecule exists as diatomic, and since all these atoms have small atomic radii, we expect stronger repulsion between these bonds. So electrons will be going this side and electrons will be going this side. And if you are bringing in again electrons, that's opposition. So this incoming electron is going to experience less attraction from the fluorine atom nuclei than the repulsion on the electrons on their shells. So we expect less energy to the incoming electron to be less attracted, and once it's less attracted, less energy is always given off. So let's proceed from the laboratory preparations of halogens. And halogens is another name to mean group 7 elements. So fluorine is not prepared by any ordinary methods in the laboratory. Chlorine, bromine, and iodine can be prepared, however, by the ordinary laboratory methods. Now, in your O-level, you looked at how we prepare chlorine, and that's the same experiment that we implement on preparation of others. That's why I was using general equations. Now, these general equations, X will represent chlorine, bromine, or iodine. As you are writing your notes, you are advised to write all the equations. However, since I was representing all the summary and I didn't want this video to take long, I was giving a general equation. When you are taking your notes, you are supposed to separate, and here you will be required to give 3 equations, both for chlorine, bromine, and iodine. So we looked at these experiment in O-level, and balancing these equations will also be another video. This is specifically redox reactions in physical chemistry. So redox reactions will be covered so that we understand how to balance such equations. So preparation of chlorine, bromine, or iodine, well, you'll be required to heat. Now conditions in chemistry are very important. Many students lose marks in chemistry because of conditions. This reaction can't take place without heating. So if you just say that potassium or sodium halide can mean anything like potassium chloride, bromide, iodide. That's what we call halides. Reacting them with concentrated sulfuric acid in presence of manganese for oxide. Now these are redox reactions, and we shall look at redox reactions explained fully so that we can understand how to balance these equations in the subsequent videos. Now we are saying that the action of cold concentrated sulfuric acid on a solid mixture of sodium or potassium halide is as follows. Now this is a good example of a redox reaction. Redox reaction simply means that an oxidizing agent like this is called acidified potassium manganate 7. It oxidizes the halide ion to its stable state like a gas. Let me say chlorine gas. For bromine it would have been bromine liquid, and for iodine it would have been iodine solid. But after oxidizing, it gets reduced to its lowest oxidation state. Like this is called acidified potassium manganate 7 or at potassium permanganate. So after oxidizing, it gets reduced to manganese 2. So from manganese 7, it goes to manganese 2. So this one which is oxidized, it goes to a gas from aqueous state. So these are redox reactions, and we are going to, then the subsequent video is going to be explaining how to derive them. So write down the notes and be patient with your progress. Inorganic chemistry equations have a specific way of writing them. Don't be tricked by anyone that you should cram them. So let's proceed. Now we are going to look at reactions of group 7 elements with individual compounds or substances, and we are going to begin with water. Now I want you to take note that the reactions fluorine varies the way it reacts with each and different substance, but all the other remaining 3 elements react mostly in the same way. So when you are reading this topic, always first see how does chlorine react, and just know that others are going to be reacting the same way as a group. So fluorine always varies in its reactions due to the abnormalities that we talked it has. It has the highest electronegativity and it has the smallest atomic radius. So we expect it to misbehave in some of its reactions. So let's look at the next slide so we are going to first look at reactions with water. And fluorine is going to vary in the way it's going to react with water from others. And in each and every reaction, the trend is going to proceed. So fluorine, we are saying that fluorine oxidizes water to oxygen and itself is reduced to hydrogen fluoride. Now you can either call this one hydrogen fluoride. Hydrogen fluoride is the most acceptable. You can either call that hydrogen fluoride, or since we are reacting it with water, we expect hydrogen fluoride to dissolve in this water. So some books you are going to find that it's going to react it's going to be reduced to hydrofluoric acid. It's the same thing because we expect this hydrogen fluoride being produced to react with the water to form hydrofluoric acid, but this is the most acceptable compound. As stated, you've said that fluorine oxidizes water. and after oxidizing water it gets reduced to hydrogen fluoride gas. And you have said that some books here you are going to find that they are writing hydrofluoric acid, so this one will turn from a gas to aqueous, and that's very key because this hydrogen fluoride gas which is produced, sometimes it combines with this water to give us hydrofluoric acid. So either way both students are going to be correct. And after oxidizing water, it oxidizes water to oxygen gas, and itself after oxidizing it gets reduced to hydrofluoric acid. So take note of the balancing and practice these equations because group 7 equations are the easiest and they are not many. So you can sit down and write all of them in the same day. Looking at other elements, fluorine, chlorine and bromine. Now I want to take note that iodine does not react with water. It's almost insoluble. Remember, iodine exists as a solid. Chlorine bromine react with water, forming corresponding hypohalous and hydrohalic acids. For chlorine, it will form hypochlorous acid and hydrochloric acid. But for bromine, it will form hypobromous acid and hydrobromic acid. Now, here I only gave the equation for chlorine. So, as a learning student, I say they are going to act the same way. What's going to vary is the major element. So, use this equation so that you can form the equation for bromine. That means that this is going to be Br bromine, and bromine exists as a liquid. So its state is liquid. So wherever you are seeing chlorine, you substitute with bromine because they react the same way. Bromine. So here we are saying that iodine does not react with water. And the reason for this is because of its largest atomic radius. Now iodine, we say that there's a question that can be posed. Why is iodine existing as a solid at room temperature whereas fluorine is existing as a gas? Now in that question, we say that earlier on when we are beginning that these are simple compounds with simple molecular structures, and we say that simple molecular structures are always dependent on the molecular size of they are always held by van der Waals forces, and in turn van der Waals forces of attraction, their strength or their magnitude. So strength means the same thing as magnitude. Their strength or their magnitude depends on the molecular size of the element. So why does fluorine exist as a gas whereas iodine exists as a solid? The reason for that is because fluorine, both of them have simple molecular structures and they are held with weak van der Waals forces of attraction, which depend on their molecular size. But fluorine, having the smallest atomic radius with its highest electronegativity, it has a very low molecular size. So the van der Waals forces of attraction holding its structure are very weak. That means that it can easily be overcome at room temperature to exist as a gas. But in iodine, having the largest atomic radius, it has also the largest molecular size. That means that the van der Waals forces of attraction in iodine are going to be the strongest. That means that iodine, the stronger van der Waals forces of attraction in it cannot easily be overcome or broken at room temperature. That means that it will continue existing as a solid. So let's proceed. We are going to look at reactions with alkalis. And here when I say alkalis, mainly it's sodium hydroxide, but also potassium hydroxide applies too. So let's start with direct alkalis, like direct sodium hydroxide. That's why I was using ions in this statement. So you're saying that fluorine reacts with, now I said fluorine is the only thing that's going to vary in these reactions. That's why you're saying that fluorine is having its own equation. And the other two, I grouped them, chlorine and bromine. I grouped them individually. But also applies for iodine. So fluorine has its own reaction, and all these other ones have their own reaction. Let's start how fluorine reacts with dilute sodium hydroxide or any dilute alkali. We are saying that fluorine reacts with cold dilute alkalis to form a fluoride, oxygen difluoride, and water. So you are supposed to see how the equation is being balanced. When you are balancing equation, make sure that you start by balancing charges. Balance charges first when you are dealing with balancing equations for alkalis. I'm going to mention this in the next video, such that we are going to make a separate video explaining how to balance alkalis, conditions for balancing them, and full explanations. But let's have a brief review about it. When you're balancing an equation involving sodium hydroxide, first of all you balance charges, and you balance charges using the hydroxide ion. So if you look at this side, assuming that we didn't have these two, the two was not there and these two, we are not seeing it, but we just wrote this equation that fluorine gas is reacting with hydroxide ion from sodium hydroxide, and we know the products that are being formed, that we are going to form fluoride and oxygen difluoride and water. So what we shall start with is balancing the charges. Now you will see that charge here is -1 and charge here is -1. Now you go to the major atom, which is fluorine. So fluorine here you find that it's 2, and this side you only had 2 here and 1 here. So how can you make this even? We normally, when you're balancing equations, you look at making things even. So fluorine on the oxygen attached to the oxygen atom was already even, but this one was not even. So that's why we placed here a 2. Now when you place here 2, notice that the charges changed. So the charge went to -2. Now here, that means that you first have to immediately balance the charges. That's why we came here immediately and replaced a 2. So we go back to our atoms. Fluorine, how many atoms are there now? We have in 4 this side. So which digit can you put this side to get a 4? That's why I placed 2 here. After doing that, you balance the number of oxygen atoms. Now on the left hand side, you'll be seeing that you're having 2 oxygen atoms. By this side, you'll be seeing that we are having how many oxygen atoms? There is this oxygen atom attached here on oxygen difluoride, and also this on water, which makes it 2. So 2 oxygen this side, 2 oxygen this side. That means that the equation is balanced. And then lastly, we always balance hydrogen lastly. So you find that there are 2 hydrogen on the left hand side. What about this side? There are also 2 hydrogen on the left hand side. But we shall make a separate video that separately explains on how to balance equations, because that's the reason why most students are running away from inorganic chemistry. So you're saying that chlorine, bromine, and iodine are all going to react the same way, and they are going to give us an halide, hypohalite, and water. So how do you read this? So I told you, here you presented my equations with x, but as we are taking your notes, for those of you who are taking them, make sure that you write you replace x with the individual elements. So that means that here it will be chlorine. Chlorine will be reacting with 2 moles of hydroxide ions to give me the chloride ion, and this is called the chloride, and water. So take note of how the equations are written, and instead of x, when you're taking your notes, make sure that you replace it with the element. Now in proceeding, we are going to look at balancing reactions of group 7 elements with hot concentrated alkalis. And now, in this video, we say that you're always going to put fluorine aside, implying that it reacts in a different way from other elements. So you're saying that two moles of fluorine gas will react with 4 moles of hydroxide ion from sodium hydroxide or any alkali to form 4 fluoride ion and oxygen gas plus water. Now notice that in these equations I'm using ionic equations, but you can either use the normal equations that are not in ionic form. So this will be sodium hydroxide in case it's specified, and this will be sodium fluoride in case it's specified. The balancing will always remain the same. Now, if you don't understand, you are free to write in the comment section about why you need more explanations from. So now let's go at this tricky equation. Now for group 7 with concentrated alkalis, this is the equation that causes a lot of confusion to the students. But what you shouldn't forget, when you're reacting chlorine, bromine, and iodine with hot concentrated sodium hydroxide, we always first start by putting here a 6. This is where you start balancing equations from. Make sure that you are putting here a 6. Some students have gone far ahead by saying that they will memorize that this side we are having 36 as in ratio. This is 3 to 6. But make sure that you're always having a 6 on the hydroxide ion, because that's where it's going to get simpler. So assuming other variables were not present, let's say that the balancing here was not present, the balancing here was not present, and the balancing here was not present, and you have ensured that you are putting a 6 here. Now we say that when you're balancing equations involving alkalis, we always start with charges. So after putting a 6 here, then we go straight away to balancing charges. So you find that we're having this negative XO3 here, and things that attach to oxygen, you first wait to balance them. So we find an individual ion that can help us balance the charge. So we already have -1 this side. That means that we need -5, and that's why we placed here a 5. So that we are having -6 on this side, and we are having -6 total charges this side. Now we are going to look at this explanation more in depth in our next video. And after balancing charges, you now go to the balancing of the individual atom, the major elements like chlorine or bromine or iodine. But I've told you the balancing is going to remain the same. That's why I represented both of those 3 elements with X. But for you, as you are taking your notes, you are supposed to write the respective elements. So after balancing charges, let's go to the balancing of the individual or the major element in the equation. So you find that we're having there's 5 X ion, like I've told you, it can either be chloride, bromide, or hydride. And this 5 plus this one here, the sum will be 6. So we go to this side so that we can get a 6 too. And you find that to get 6 atoms this side, we shall multiply this molecule by 3, so that we are having 6x. So left hand side atoms of X will be equal to right hand side atoms of X. After balancing the major elements, you go to oxygen. Now this side, how many oxygen atoms are we having? This side you're having 6 oxygen atoms. Now I want you to always remember that we balance oxygen using water. The side that lacks enough oxygen atoms is where we add a given number of water molecules to balance up the equation. So note that here we're having 6 oxygen atoms. So what about this side? Now this side, remember, we had without the balancing on the water, you would consider that we had 3 oxygen and 1 oxygen in water. So this side we're having a total of 4 before balancing, but we need them to be 6 like this side. So what shall we do? We shall we go on water molecule. It's the water molecule that we use to balance oxygen atoms. So on the water molecule, how many oxygen atoms do we need? So here we are having 3. That means that I need 3 oxygen atoms. That's why we placed a 3 above there on water. So water has already helped us balance the oxygen atoms. Now lastly, it's always hydrogen that's balanced the last. And when we are going to proceed to subsequent topics, and you are going to see that the side that lacks enough hydrogen atoms, we add hydrogen gas. But we shall explain that more in depth in the next video. So balancing hydrogen, the left hand side has 6 hydrogen atoms. What about the left hand side? So we are seeing that the left hand side also has 6 hydrogen atoms. So that means that this equation is already balanced. And the way they are marking inorganic chemistry equations, they give 1.5 a mark. But you must first make sure that you give a statement which is in this form with its corresponding products, because also this one carries a mark. For each and every equation presented in inorganic chemistry, as you're answering your paper, the statement and both the equation carry marks, so don't underestimate any of them. Let's look at displacement reactions. Now displacement reactions, you looked at them in O level, so here we are just flashing back. So you find that among group 7 elements is fluorine that's the most oxidizing. However, it would have been fluorine, but fluorine does not engage in most of the laboratory reactions. So we always look at chlorine as being the most oxidizing gas, and the reason behind that is due to its small atomic radius and the high electronegativity it has over other elements. So we expect that in a solution, if we bubble a greenish yellow gas in a brown solution of bromide or any solution or any compound or a substance or a solution having an ion of bromine, which is a bromide ion, we expect chlorine gas to oxidize it to its stable state. So bromide ion gets oxidized to bromine as a liquid. That's why we're putting it in aqueous. And after oxidizing, it gets reduced. That's why we are saying that when chlorine is bubbled through an aqueous solution of potassium or sodium bromide, the colorless solution turns what? Turns reddish brown. Now these are very common questions in MOFs and UNEB questions. They are going to first tell you that chlorine was bubbled through an aqueous solution of potassium or sodium bromide. Then ask you state what was observed. You need to start from the initial color. Even in practicals, chemistry, you always start from the initial color. That's why we are saying that the colorless solution turns reddish brown, because the color of the color of bromine is reddish brown. Now what happens to the iodine is the same case. There is also going to be redox reaction where chlorine is going to oxidize the iodide ions to iodide ions are going to go to iodine, and chlorine gas after oxidizing it gets reduced to chloride ions. So these are simple equations you can learn and master how to balance them by continuous practice and assessment. But here when you are doing such questions, the observation is key. I said you must start from the original color of what you are seeing. That's why we are saying that the colorless solution, so this is the initial color. Let me highlight it. This is the initial color, the colorless solution. This is the initial color. Turns, now this is the change, turns brown, because iodine is browning solution in color. And the student who writes here solids won't be denied a mark. So let's proceed. We are looking at other oxidation reactions involving group 7 elements. Now we said group 7 elements are the same as halogens, and here we are saying halogens act as oxidizing agents by accepting electrons from reducing agents. As you covered it in your O-level, we say that oxidizing agents after oxidizing they get reduced because they are acceptable to electrons, and those electrons are provided by reducing agents as already stated above and clear. So let's proceed to the next slide. And in this video we are going to look at how we can implement some of the idea we have talked previously about in the previous slide. So we are looking at the oxidation power of iron 2 and 3, and I've told you chlorine is the most oxidizing gas in group 7 elements or halogens. It could have been fluorine, but fluorine does not engage in most of the reactions in the laboratory. So let's look at some of the factors influencing that. Now we are saying that for anything having a low oxidation state, which has more than 2 oxidation state, always chlorine is going to oxidize it to its major oxidation state. That's why we are saying that when chlorine is bubbled in a solution of iron sulfate, the pale solution. Now notice that this is where the question we are going to ask you starts from. In the part A is going to tell you that, tell us your observation. You can't tell us you formed any compound. What observations about colors? So simply I told you begin from the initial compound you are seeing. So the pale solution and its pale what? So iron to ions are always green. So pale ground solution always turns yellow. So I missed brown here. So pale brown solution turns yellow or pale yellow. And that yellow is due to formation of iron 3. And the reason behind that we are saying this is because of oxidation of iron to ions to iron 3 ions. I've said reason being chlorine gas is a strong oxidizing gas, and the reason for that, for chlorine being a strong oxidizing gas, is due to its small atomic radius and highest electronegativity. We are saying that bromine has a similar reaction but not iodine. So you find that iodine is not having a similar reaction. Why is that the case? Iodine has the least electronegativity due to its largest atomic radius. Let me hope that is understood and noted somewhere. So let's look at oxidation of hydrogen sulfide. So always hydrogen sulfide is oxidized to a sulfur solid. Now most questions like this question. They like this question because students get confused of what's being formed, and some pamphlets are missing out some of these critical or important elements. So we shall keep bringing back these elements to test your understanding. So we are saying that when chlorine is passed through a gas containing hydrogen sulfide, and this is a gas, take note that this is a gas, or sometimes can be a solution. It becomes a solution when we dissolve it, hydrogen sulfide, in water, just like I explained for the case of hydrogen fluoride gas. When hydrogen fluoride gas is dissolved in water, it forms hydrofluoric acid. When hydrogen sulfide gas is dissolved in water, it will form hydrogen sulfide in a solution state. I don't know whether it has any solution concerning acids. So most questions will ask you, chlorine gas was passed through a gas jar containing hydrogen sulfide. Give what was observed. Now I want you to note that my observation I'm giving here are about solutions. But if you want to bring out the true chemistry that you require, you must state also the color of chlorine. So someone can tell us, a good intelligent student can tell us that. Now since we don't want to say any chemical name in your observation, So it give us the color of chlorine gas. So a yellow greenish gas dissolved in the Kali solution of hydrogen sulfide, forming yellow solids. Now this word of deposit eliminated. I think it was a mistake. Instead of deposit, write formation. Deposit, you have eliminated it in chemistry. We believe that deposits are for mobile monies and banks. We don't do transfers in chemistry. So the deposit, this word is highly condemned in chemistry for your syllabus. So a yellow solution forms the Kali solution will form yellow solids of sulfur, and this is a perfect example to explain that explanation. So take note of that chlorine is going to react with sulfur, the sulfide. Now this sulfide is after dissolving this hydrogen sulfide in water, because this is the question that we are going to ask you, and we want you to write this very equation. You will be awarded 1.5 mark, showing that chlorine will oxidize the sulfide and to form yellow solids of sulfur. So these are the yellow solids. Sulfur exists as a yellow solid in nature. Then plus chlorine, after oxidizing, it will turn to an ion. So let me first remove this highlight so that you see it. After oxidizing, it gets reduced to ion because it becomes acceptable to electrons. So a good student will take this equation the most, because you're going to mainly question this one. Now this one is good if at all we have given it to you in paper 1 and we tell you to write the equation. So it's going to be the same statement. Now moving on, let's look at oxidation of sulfur dioxide still by the same gas, which is chlorine. Because chlorine is a very strong oxidizing gas, so we are going to be looking at most of its reactions, even in physical chemistry, which is the next video which will be uploaded, which is about balancing redox reactions and how to deal with redox reactions. Now the knowledge which will be got from that topic is going to help you tremendously boost your inorganic chemistry approach, and it's going to change the way you're viewing inorganic chemistry. So in most of these, if you see an equation having three ions on each and every side, most of those equations are redox reactions. They are involving both oxidation and reduction. And we said, for now, you can take the notes and we are going to explain how they are balanced in the next video. So I'm going to skip that for the next video, so that when we come back we can learn how step by step how we can balance such equations. I told you every equation in organic chemistry is balanced in a specific way. So let's proceed. Now in this slide we are going to look at some of the other reactions involved in chemistry. Now we are going to look at this common. In fact, you should put here an NB on these notes on this slide. Iodine oxidizes sodium thiosulfate to sodium tetrathionate. Now you don't need to master this. You don't need to master how we name this compound. What you need to master is how the equation is written, because this is an equation you are not going to avoid in your A-level chemistry. So make sure that you now write this equation. And it's an oxidation equation that is not complicated. The complicated ones I told you are the ones where you're having three elements this side and 3 elements this side. Those are what we call redox equations. So in the next video we shall be looking at how we learn how to balance them. So let's look at the compounds of group 7 elements. Then we start with how each of them is prepared. We are going to look at hydrides of hydrogen fluoride. How is an hydride of hydrogen fluoride prepared? And we are saying that hydride of hydrogen, the hydride of fluorine is prepared by distilling calcium fluoride with concentrated sulfuric acid. So what you should note here, or what you should underline here, that is prepared by a process of distillation. So that you must not miss out on your answer. Calcium fluoride with concentrated sulfuric acid. Now in organic chemistry, we measurize conditions. So a student who says distilling calcium fluoride with sulfuric acid is wrong. You can only be correct when you are presenting the condition in which sulfuric acid is in. So take note about that. Then you write the equation. These equations are simple, I told you. They just involve exchange of ions. So calcium gets this ion on the sulfate ion from calcium sulfate, and hydrogen gets this fluoride ion from the hydrogen fluoride gas, which we need. And we say that this hydrogen fluoride gas, since in water, when it gets dissolved in water, that's why it turns to hydrofluoric acid. And I told you that's why you will find some textbook telling you that hydrogen fluoride at times is hydrofluoric acid. So don't be confused. They are all the same things, and you won't be penalized if you write any. Now let's proceed to the hydride of chlorine. The hydride of chlorine is called the hydrogen chloride, and this in most cases is a gas. Now there are so many procedures of how we can prepare hydrogen chloride gas, but one of the major ones and the most acceptable is by using brine or sodium chloride in concentrated sulfuric acid. But this concentrated sulfuric acid must be cold. In fact, if you feel like you forget this stage, you can simply say that concentrated sulfuric acid reacting with solid sodium chloride, and once you react them, you get sodium hydrogen phosphate. Note this. Take note of this. Sodium hydrogen sulfate and hydrogen chloride gas, which we need. Now the reason why we are not forming sodium sulfate is because the temperature at which sodium sulfate is being formed is very high, so it cannot be formed on the laboratory basis. So sodium sulfate, equations involving formation of sodium sulfate, you'll find them in your practicals. But theoretically, we shall be forming mainly hydrogen sulfates of group 1 elements. And we are saying that hydrogen chloride is also manufactured by direct combination of hydrogen and chlorine. I didn't say the equation for this, but you can apply it in this area. We say that hydrogen chloride can be converted to hydrochloric acid by dissolving it in water. Like I've been telling you that the hydrides of these elements, you can either call them hydrides or you can take them to acid. They all mean the same thing, especially when you are going to be explaining acidic strength. Some textbooks will explain it in terms of acids, and others are going to explain it in terms of gases. And gases, I mean they are hydrides. So if you look at Roman number 3, we are looking at hydrogen bromide. Now we are saying that hydrogen bromide and hydrogen iodide, this can be prepared by action of water on phosphorus tribromide or phosphorus triiodide. Now I didn't put the equations here, but you can include them having any textbook. I believe that's something minor. So let's look at some of the properties of the hydrides of these group 7 elements. Now here we are going to first look at boiling points, and I've told you boiling points is the same as melting points. So if you see me explaining boiling points, just know that it's the same explanation with melting points. And what I emphasize the most is, when you're looking at boiling and melting points, first of all, you need to note down the structure. And we looked at that, and we say that structure of the group 7 elements together with their compounds, they are held by, they possess simple molecular structures. And after knowing the structure held by the compounds, you are supposed to know the forces holding that structure. And the forces holding such structures are called van der Waals forces of attraction. And after knowing that, then how are you going to differentiate them? Van der Waals forces of attraction, their strength or magnitude depend on what? Quick question. So Van der Waals forces of attraction depend on the molecular size. So you find that hydrogen fluoride or hydrofluoric acid, wherever we are going to use, I've told you they are the same things. Hydrogen fluoride is going to have the lowest boiling point, or it's going to have an abnormally low boiling point because of the abnormalities in the fluorine atom. I have already explained that, but you're going to see that hydrogen chloride is going to have the least boiling point, and then hydrogen bromide or hydrogen iodide are going to have larger boiling points. Let's transit to the next slide. Alright, so now let's proceed with the explanations that I've just given. So they are telling us that the boiling points of the hydrides increase in this order. Now next that when you are being asked the order in which boiling points increase, there we use less than signs. So boiling point of hydrogen chloride is less than boiling point of hydrogen bromide, and boiling point of hydrogen bromide is less than boiling point of hydrogen iodide. Similarly applies to the boiling point of hydrogen fluoride. Now the explanations are going to remain the same way like I've just explained in the previous slide. Now here you are saying that all these elements are having simple molecular structures. Now these simple molecular structures are having what? They are held by van der Waals forces of attraction. Hence, the energy required to separate these molecules, hence increasing energy. Now I skipped some parts here to make this explanation elaborative. I said, now what's going to be varying here? The ions are going to be varying. So we say that chlorine atom is having less energy than there's low bonding energy in hydrogen chloride because the chlorine atom is having a smaller atomic radius than the bromine atom in hydrogen bromide. That's why that means that hydrogen bromide has a larger molecular size. And once hydrogen bromide has a larger molecular size, that means that the van der Waals forces of attraction in it are greater than that one in hydrogen chloride. That means that hydrogen bromide will have a higher boiling point than hydrogen chloride. Similar applies to the hydrogen iodide and hydrogen bromide. Iodine in hydrogen iodide has a larger atomic radius. That means that it has the highest molecular size, and once it has the highest molecular size, the van der Waals forces of attraction it are going to be stronger. Once they are stronger, that means that its simple molecular structure is also going to be stronger. That means that the boiling point is also going to be very strong. Now we are going to look at abnormalities. Abnormalities is hydrogen fluoride. Why is hydrogen fluoride having an abnormal boiling or melting point? Now we are saying that hydrogen fluoride has the highest boiling point, even though it has the smallest molecular mass. Now this goes against what we have just explained, because we say that things having simple molecular structures, the van der Waals magnitude or strength of the van der Waals forces of attraction depend on molecular size. But hydrogen fluoride is having the smallest molecular size, but it's having the highest boiling point. And why is that the case? I told you when you see such a question, we always refer back to periodicity. So we shall talk about smallest atomic radius and electronegativity. That's what's going to be in the explanations. And we are saying this is due to hydrogen bonding. Yeah, this is a good thing. Hydrogen bonding is a good factor, but we use this one mostly in acidic strength. So hydrogen bonding. Hydrogen bonding refers to the bonding between the hydrogen atom and a highly electronegative element in the periodic table. There are only three most electronegative elements in the periodic table. We have nitrogen, we have oxygen, and finally we have fluorine. So hydrogen, when we have a hydrogen atom connected to a nitrogen atom, we can call that hydrogen bonding. And when we're having hydrogen atom connected to oxygen atom, this is also hydrogen bonding. And when you're having hydrogen atom connected to a fluorine atom, this is also hydrogen bonding. So we shall look more in depth about this one in physical chemistry. But hydrogen bonds are very strong and they require a significantly higher amount of energy to break them. So that's one of the reasons why hydrogen fluoride is having the highest boiling point. But also, we are saying that fluorine is highly electronegative, which I've just talked about. This is fluorine as an atom. And being highly electronegative is because it has the smallest atomic radius among other atoms in those hydrides. And that's why you're saying that's its formation of very strong intermolecular hydrogen bonds. The smallest atomic radius of fluorine atom, together with this hydrogen bonding that I've explained, I've said there are types of hydrogen bonds are found by three elements, and those elements are highlighted in red in your periodic table, which is nitrogen, oxygen, and fluorine, showing that if you go to the periodic table and you look at them, they are in red, which implies that they are the most electronegative elements on the periodic table. So once hydrogen atom connects to them, we expect to form hydrogen bonds, and those hydrogen bonds, like I've said, they require a very high amount of energy to be broken. That's why hydrogen fluoride is having, that's one of the reasons why hydrogen fluoride is having the highest boiling point. Now let's go to concept number 2. We are going to look at acid strength. Now here what I want you to add, you can add it up here. You can say that, first say that acid strength depends on ease of release of hydrogen ions in solution. Acid strength depends on ease of release of hydrogen ions in solution. Now, since acid strength depends on ease of release of hydrogen ions in solution, what are you going to look at? We are going to look at, because for hydrogen ions to be released in solution, this bond between the hydrogen atom and the fluorine atom must break. So we are going to look at which one will have ease in breaking the bond, and we are going to refer back to bond energy in our explanation. But also at some point we are going to look at hydrogen bonding because we are having hydrogen fluoride. So we are saying that acid strength increases in this order. Hydrogen fluoride is having the lowest. I said you can call this one hydrogen fluoride or hydrofluoric acid. You can call this hydrogen chloride or hydrofluoric acid, they are the same. But I'm going to use hydrogen fluoride, hydrogen chloride, and hydrogen bromide, and hydrogen iodide. So you're saying that acid strength increases in this order. Hydrogen fluoride is less than hydrogen chloride, and hydrogen chloride is less than hydrogen bromide. So we are saying that this is because the acid strength is increasing in this order. Hydrogen fluoride is less than hydrogen chloride, and hydrogen chloride is less than hydrogen bromide. Hydrogen bromide is less than hydrogen iodide. Why is this the case? This is, I said, you begin with acid strength depends on ease of release of hydrogen ions in solution. Then that's, whenever you're answering such a question, that's what you should begin with. So you put a note here. Okay, let's begin. So we are saying that acid strength is increasing in this order. What's the reason behind that? We are saying that the reason behind that is because the bond strength of the hydrogen halogen bond, like I've notified here, the ease of release of protons in solution is going to depend on how easily this bond is broken. And we say that the shorter bonds are the strongest and the longer bonds are the weakest. So we are saying that this is because the hydrogen halogen bond, the strength of the bond between hydrogen and hydrogen decreases in this order. Hydrogen fluoride greater than hydrogen chloride, hydrogen chloride greater than hydrogen to bromine bond, and the rest. So that the ease of the proton is, a proton is the same as the hydrogen ion. So we are seeing so that the ease of hydrogen ion or proton is what increases from hydrogen fluoride to hydrogen iodide, hence increasing the acid strength. Now, what is going to determine the strength of the bond between the hydrogen atom and the halogen atom? It's going to be mainly atomic radius. So fluorine, since it has the smallest atomic radius, it's going to form a shorter bond between hydrogen and its atom. That means that since the bond is shorter, it's going to be more stronger. And on top of that, I've said fluorine is one of the most electronegative elements on the periodic table. So fluorine is going to form hydrogen bonds. So hydrogen bonds are very strong to break. So the bond between fluorine atom and hydrogen atom is going to be very strong. That means that these hydrogen ions are not going to be easily released in solution. And once few hydrogen ions are released in solution, that means that the acidic strength is going to be very low. That's why we are going to say that hydrogen fluoride or hydrofluoric acid is going to be the weakest acid among all these ones. Now, let me compare it with hydrogen iodide. Why is hydrogen iodide going to have why is it going to be the most acidic? Hydrogen iodide is going to be the most acidic, reason being iodine is the last element in group 7. And the last element in group 7, that means that it has the largest atomic radius. Once it has the highest atomic radius, that means that the bond length between the iodine atom and hydrogen is going to be long. Like we said earlier, the longer the bond, the weaker it is. So that means that this bond is going to require less amount of energy to be broken. So the bond strength between hydrogen and iodide atom is very low. So since it requires very low amounts of energy to be broken, in solution, hydrogen iodide is going to release the most hydrogen ions. So hydrogen iodide there will be more protons in a solution of hydrogen iodide. That means that it's going to be the most acidic. That's why here we are saying that the decrease in bond strength is due to increase in atomic radius, which increases bond length, thus weakening the bond in the same order. But I hope I've explained that in more details. Looking at the part 3, we are going to look at hydrides of group 7 elements as reducing agents. So these hydrides are going to be reducing agents. Now this is a most common question in UNEB. And we examine it practically, but we examine it indirectly. So we are saying that hydrogen fluoride and hydrogen chloride gas are not reducing agents. So we need to see this statement when you're writing it. The only hydrides that are present, so this statement will carry a full mark because we shall tell you to describe the reactions of the hydrides of group 7 with concentrated sulfuric acid, and note that the hydrogen fluoride and hydrogen chloride won't react. The reason for that is because the fluorine atom and the chlorine atoms in them, they having small atomic radius. So their bonds are strong. They cannot easily break to engage in other reactions. But if you look at the hydrogen bromide and hydrogen iodide, the individual atoms of the halogens have large atomic radius, implying that they form longer bonds, which are weak and they can easily break to react with other elements. That's why we are saying that concentrated sulfuric acid oxidizes both hydrogen bromide and hydrogen iodide to their respective elements. So hydrogen bromide, after being oxidized, it forms hydrogen bromide. After being oxidized, it forms a bromine gas, and the acid itself is reduced to sulfur dioxide and water. So take note of this reaction. It's a very commonly asked question in UNEB and in mocks. If you're having no notes, you can start it, or you can go back and you discuss it with your members. And if you're not having any member following up this notes, try to share the link of the video so that you can benefit as a family. Now similarly, like we have looked at the reaction between hydrogen bromide and concentrated sulfuric acid, hydrogen iodide also has the same or similar reaction. Hydrogen iodide gets oxidized to iodine, and sulfuric acid gets oxidized to sulfur dioxide gas and water. Now these questions are tricky. In such a way that we are going to first ask you, what is the observation? Now let's start with hydrogen bromide. You are going to see a reddish brown vapor, and with iodine you are going to see a purple vapor. I think I didn't include the observations in my statement, but you can refer back to your practical books. You'll be seeing this reaction. I've told you it's examined practical and theoretical, so it's a very important equation to note. And if you haven't understood it, I advise you to go to your practical book and try to watch it the way it's being examined. We always tell you to add concentrated sulfuric acid and warm that part. So with hydrogen bromide, we expect you to see a reddish brown vapor, and with hydrogen iodide, we expect you to see a violet or purple vapor. I think that has been understood. So let's proceed to the next part. We are going to oxides and oxyacids. Oxides and oxyacids, one of them we have for chlorine. We have chlorine 1 oxide. Chlorine 1 oxide reacts with water to form hypochlorous acid. This one I've already explained it. And chlorine 4 oxide reacts with water to form the individual acids together. These are disproportionation reactions. We shall look at this later in transition methods. But this reaction again is also very important. This reaction is very important. It's widely asked both in mocks and in UNEB. So make sure that you understand it. Chlorine 7 oxide, you can put this one as an NB. Chlorine 7 oxide reacts with water to form the chloric 7 acid. It's a very important reaction and it's not difficult. What you need to master is chlorine 7 oxide reacting with water to form this chloric 7 acid. So note this down and borrow it somewhere, or if you're having a summary, make sure that you discuss and master it properly. So let's proceed. Let's proceed on the acid strength of the oxyacids. Now, what are oxyacids? Oxyacids refers to the halides of group 7 elements but having oxygen atoms attached to them. Like I told you earlier on, oxygen is one of the most electronegative elements in the periodic table, and that's why it's highlighted red on the periodic table. So we say that acid strength always depends on ease of release of protons in the solution. Now we are going to explain this more in depth in physical chemistry, but here you are going to have a hint. And what the concept here is, oxygen is a more electronegative element. Now oxygen is always withdrawing bonding electrons. Oxygen is always going to be withdrawing bonding electrons. The more number of oxygen atoms, the more acidic that compound becomes. So we expect this one with the largest number of oxygen atoms to have the highest acidity, followed by this one, and then this one lastly. And then we are saying that, first of all, when you're explaining acid strength, always start with a statement that acid strength depends on the ease of release of protons in solution. That's the first step. Then we are saying that acid strength increases in this order. And the reason for that is because this is due to increase in the number of oxygen atoms bonded directly to the chlorine atom. And we are saying that oxygen is more electronegative compared to chlorine. The more that's why we are saying that since oxygen is more electronegative compared to chlorine, it is going to withdraw the bonding electron towards itself. Like you draw those bonds. If you are to draw these bonds, now this is not the actual structure, but let me give you a primary understanding. When you are drawing these bonds, we draw them this way. Chlorine is going now to be attached to these oxygen atoms. Now, I'm just giving you a primary standard inorganic explanation, but we are going to look at more in depth of this science in physical chemistry. So, when we are saying that oxygen is more electronegative than chlorine, once it's more electronegative, that means that it's going to withdraw bonding electrons towards itself. Let me hope you understand. These are bonding electrons. These bonds you see are called bonding electrons. So once it is withdrawing bonding electrons towards itself, these bonding electrons also here, this bond is going to weaken. This bond is going to weaken because electrons are being pulled this side. So in organic chemistry, this one is going to attain a partial positive, and this one is going to attain a partial negative. The more bonding electrons are pulled towards oxygen atoms, the more the partial negative here increases, and the more the partial positive here increases, and the more the bond between these atoms weakens. So once the more the number of the oxygen atoms increases, the more this bond weakens. I've already explained because of this increase in partial negative and partial positive on the chlorine atom and the hydrogen atom. So that's why we are saying that increasing the number of oxygen atoms, since they are electronegative, they are going to be increasing the tendency of attracting bonding electrons towards themselves, thus weakening the hydrogen to chloride bond. And once it's weakened, this bond is going to be easily broken. And once it's easily broken, protons are going to be easily released in solution. And we say that acid strength depends on ease of release of protons in solution. The higher the number of protons released in solution, the greater the acid strength. And the less the number of protons released in solution, the lower the acid strength. So assuming that it was only one oxygen atom, if it was only one oxygen atom, that means that the attraction of the bonding electrons was going to be low. That means that there will be a less partial negative on the chlorine atom, and there will be a less partial positive on the hydrogen atom. That means that few hydrogen ions, this bond was going to be relatively stronger, and few hydrogen ions were going to be released in solution. Hence, acid strength would have been low. Let me hope that has been simple to understand. So for those of you who are not understanding properly, you can either stop the video and replay it back to master this concept, because it's a very critical concept. So let's proceed to the next slide. So proceeding with the explanation, we are saying I've already explained this one. So I've already explained all this. I've already explained all this and how they come about. So you're supposed to go through, try to understand the notes, try to replay what I've said earlier on and understand those notes. So let's look at some of the reactions involved with chlorine. Chlorine, we have said, is an oxidizing gas. So it oxidizes all elements to their uppermost stable oxidation state. For aluminium, it only has one oxidation state. So aluminium is oxidized by chlorine to aluminium trioxide, and iron has two oxidation states. There is iron in the +2 oxidation state, iron in the +2 oxidation state, and iron in the +3 oxidation state. But since chlorine is most oxidizing gas, it will oxidize iron to its most upper stable oxidation state. So instead of iron 2, we shall form iron 3 chloride. Now in the questions, we usually tend to be stubborn. especially in UNEB and more questions. Then we shall ask you, how are their lowest possible oxidation states prepared? Now, chlorides of their lowest possible oxidation state are prepared using hydrogen chloride gas. That's why we are telling you iron has two oxidation states, the +3 and the +2. When you hit it directly with chlorine, it's going to take it to the upper one. But how can we get the chloride of the lower one? That's why we are using hydrogen chloride gas, because hydrogen chloride gas is a non-oxidizing gas. So we are saying that hydrogen chloride reacting when you heat aluminium with hydrogen chloride gas, you are going to get iron 2 chloride. Now there is plus hydrogen gas here that I didn't include it. Hope you recognize that mistake. There is plus hydrogen gas on each of them. So similar applies to tin. You covered group 4 elements, and group 4 elements also have two oxidation states. There is the +2 oxidation state and there is the +4 oxidation state. So we look at how, if we heat it directly with chlorine, we shall get tin 4 chloride, which is a covalent liquid. But how can we get tin 2 chloride? We shall use hydrogen chloride gas, because chlorine is oxidizing, but hydrogen chloride gas is a non-oxidizing gas. So let's proceed. We are saying that some of the insoluble chlorides of chlorine can be prepared by precipitation method, and this is your qualitative analysis work. Let me hope everyone has the practical book to refer to those notes. You have been doing this precipitation method ever since your O-level practicals, where we tell you that to a solution containing electrons was added, let me say, dilute HCl, state what was observed. So you'll be seeing white precipitate. Alkalis solution from the white precipitate. I've told you chemistry, you always start from the initial. Initially it was a alkalis solution, and after adding HCl you form a white precipitate. That's why I'm presenting my observation as alkalis solution forms a white precipitate. Now let's go to the next heading, and this is the most commonly asked question in paper 1 chemistry. What are the unique behaviors of fluorine? After doing that, they're asking you for reasons. You always refer to periodicity. Reasons will be fluorine has the smallest atomic radius, fluorine has the highest electronegativity, fluorine has the lowest bond dissociation energy. You always refer back to periodicity. There's no you can, for as long as you see the word Y or you see the word reasons. But when you are seeing ways, like here in our next heading, so let's go to the next slide and you see why fluorine differs from the rest of the group. Now most students confuse this one with ways in which fluorine differs from the rest. I've said when you see why or reasons, you always refer back to periodicity strictly. Since we are referring to reasons, that's why I've talked about periodicity, because there was a why. When you see why or reasons, that you always refer back to periodicity. That's why I'm saying that fluorine has the smallest atomic radius. Fluorine has the very high electronegativity. Fluorine has the lowest bond dissociation energy. Like I've already said, answering these questions also depends on the question setting. Now this one, if the question says why does fluorine differ from the rest, they are comparing fluorine to other elements. You would have said here, this is due to its highest electronegativity, lowest bond dissociation energy, smallest atomic radius. But But for a question which is open, asking you for why is fluorine behaving in a different way without comparing it to anything else, you are free to write these answers I gave here. But when it's being compared to other elements, you convert high to highest, low to lowest, and small to smallest. Now proceeding to another heading. Another heading is about the properties. Now it can either be the properties or it can be ways in which fluorine differs from the rest of the group 7 elements. Now I want you to understand that for any properties or for any ways in inorganic chemistry, these are always reactions. We want you to describe a reaction in a statement. We want to see the words of form, or we want to see the word of react in your statement. Each and every statement you're having, except some few. That's why you are saying react, react, oxidizes, react, forms, react. That's what you should have in your answering. Some pamphlets most of the students are using are not emphasizing about that. Now that's why we are saying fluorine oxidizes water. Like here, you look at the reactions. All the reactions we have been looking at, you have been seeing that fluorine is having different reactions from other elements. So if we start looking at those reactions, we are saying that fluorine oxidized water, like before in the previous slides. So most of these ones are repetition of what I've explained before. So we can just go through them one by one. Fluorine oxidizes water to oxygen and hydrogen fluoride, whereas others, chlorine, bromine, form a mixture of hypohalous and hydrohalic acids. Iodine does not react with water. Fluorine reacts directly with carbon, while others do not react with carbon. Now, fluorine when it reacts with carbon, it forms carbon tetrafluoride, but you cannot prepare the chloride of carbon. You cannot prepare other halides in the same way. So fluorine reacts directly with carbon. Here you put an inverted V and say to form carbon tetrafluoride, whereas other elements do not. Next point, fluorine reacts with hot concentrated alkalis to form oxygen, fluorides, and water. We have looked at alkalis. We have said that alkalis can be sodium hydroxide or potassium hydroxide, any, while others form halides, halides, and water. So ways or properties, these ones can be ways or properties in which fluorine differs from the rest. These are always reactions that you have covered before, and that's why I brought this heading after looking at all those reactions to bring this one out clearly. Now we have seen that we have explained some of the oxyacids. Oxyacids, I've told you, they are halides of group 7 elements having oxygen atoms. We have looked at them when we are explaining acid strength. Those are what we call oxyacids. Now fluorine does not form those oxyacids, but other halogens do. Fluorine has only one oxidation state, while other halogens have several oxidation states. And in this, we are saying that you have been seeing that here we are forming halides, halides. Here we are forming hypohalides and halides. But fluorine does not form those disproportionates. It only forms one product, which are always in the same oxidation state, whereas others can form in multiple oxidation states. That's why we are saying fluorine has only one oxidation state, while other halogens have several oxidation states. Then, hydrogen fluoride is a weak acid, while other halogen acids are strong acids. And the reason behind that I've told you is due to formation of hydrogen bonding. Fluorine atom is one of the strongest electronegative element in the periodic table. So if hydrogen is one of the most electronegative atom in the periodic table, so if hydrogen atom combines to it, we form what we call hydrogen bonds. And I've told you there are only 3 elements that form hydrogen bonds. We have fluorine atom, nitrogen atom, and oxygen atoms. When hydrogen combines with one of either of these atoms, they form hydrogen bonds. That means that, and these bonds require a very high amount of energy to break. So that means that in solution, hydrogen fluoride is going to release few protons. And once few protons are released, that means that that solution is going to be less acidic. So proceeding to the next step, we are saying that hydrogen fluoride is a gas at room temperature, while other hydrogen fluoride is a liquid at room temperature. So put here an inverted V and say hydrogen fluoride is a liquid at room temperature. So there is something missing here. Hydrogen fluoride is a liquid at room temperature, while other hydrides are gases. And the reason for that is because of this hydrogen bonding. So everything comes back to bonding. The other ones are gases because their bonds can easily be broken. But this one, since it has strong hydrogen bonds, they cannot easily be overcome. So at room temperature, it's going to exist as a liquid. Alright, let's proceed. Alright, so this is a supplement of some of the qualitative analysis of the group 7 ions. Qualitative analysis, I've told you, any question set for inorganic chemistry, we shall set it in a way that part A to part C is theory. Part D is going to always be practical, especially paper 2. And I've told you, when you're stating observations, you always start from your initial observation. What's the initial color of that compound or substance you are dealing with? And it's going to which color? I've told you, I always avoid the word deposit. It's highly condemned. Deposit is used on mobile monies, so avoid it highly in chemistry. We don't have anything like deposit in chemistry. Always use the word form. So with lead to nitrate solution, these are some of the observations, and I'm not going to repeat them because you have been looking at this ever since O level. And with silver nitrate, these are the observations. Similarly, I'm not going to repeat them. Now the only new thing here is going to be bleaching powder. Now for this one, you're going to refer to your practical book. Practical books will give you the elaborative explanation, and you have to note it down here in your notes because it's asked highly in your mock examinations. For those of you who want to be good at chemistry, always when you're reading inorganic chemistry, make sure that you have your practical book aside by you, so that after reading about specific elements, you also read about the qualitative analysis part of them. So you write down this table and you make research on bleaching powder. Let's proceed to the next slide. And finally, that will bring us to the end of our video. This video has been compiled and presented to you by I personally, Wakembe Yusuf. And if you want to reach me out in anything or consultation or anything about chemistry or mathematics, you can reach me out on the following numbers. All copyrights reserved in this compilation, and we shall meet in the next video where I've decided to explain more chemistry. I want chemistry to be understood by others so that we can pass as a family. So like and share the video to your friends so as you can benefit as a team. After watching the video, make sure that you go back to the question bank, try out some numbers, comment in the comment section where you find difficulty or where you didn't understand properly. You will be assisted in the next subsequent videos. So have a good day. May God bless you. And for those of you having papers, may you have a brilliant success.